Okay, so we're still talking about the sampling distribution, but we're going to talk about the sampling distribution for sample means instead of sample proportions, and we're going to see that a lot of the math is exactly the same. So in this case, our parameter, remember that's the number that describes the population. It's going to be, we'll use the Greek symbol mu, and that's going to be the population mean or the population average. So our statistic will be a mean or an average that comes from our samples. So x bar, that's the sample mean or the sample average. So we'll use x bar when the average is describing, is coming from a sample, and we'll use mu when that average is describing the population. And remember, when you use the word mean, you're just really thinking old school average, like you're adding up all the numbers and dividing by how many there are. So the standard deviation formula, it's going to look a little bit than the standard deviation formula for proportions. So remember, for proportions, we had that the standard deviation was p times 1 minus p over n, the square root of all that. So the standard deviation for the sampling distribution of the sample means, that's just going to be the original standard deviation divided by the square root of the sample size. But you'll notice both of the formulas have a square root of n in the denominator. So there's a lot of similarities here. So in both cases, the larger the sample size, the smaller the standard deviation, since the sample size is in the denominator. So let's look at an example here. So we've got the scores on the ACT have a normal distribution, and they've got this mean of 18.6 and a standard deviation of 5.9. But now we want to look at the sampling distribution if we're sampling 76 seniors. So the mean is going to be the same as if we were just sampling, one senior at a time. The mean of groups of 76, that's going to be the same as the mean of just the single scores of all of the students. So the mean for x bar is 18.6. But the standard deviation for x bar, that's going to depend on the sample size. So that's going to be that original standard deviation, just the standard deviation of just single ACT scores, divided by the square root of 76. So in this case, that is 0.677 about. Okay, so this brings us to kind of the fundamental theorem of statistics, which is how do we use the properties of a normal distribution when a distribution itself is not normal? And the answer is that instead of just looking at individual quantitative values within the distribution, you want to look at groups, randomly selected groups, and then you want to look at like the sample mean of those groups. And it turns out that the sample means become more normal as the sample size increases. So let me write that down in words. So let's say we have just some quantitative random variable x. So we'll say x is distributed with mean mu and standard deviation sigma. So then x bar, so the distribution of sample means, will be approximately normal with mean exactly the same, and the standard deviation of the sample means will be the standard deviation of the original distribution divided by the root of the sample size. And this of course happens when you're sampling large, you're taking a large random sample, and the distribution of the sample means becomes more, the distribution more closely resembles a normal distribution as you increase the sample size. So we'll say for large n. So that is sort of the fundamental theorem of statistics. So it allows us to look at distributions that are not normal, but if we take very large samples, then the distribution of means will be approximately normal. So obviously, if we're starting with a distribution that's very heavily skewed, we're going to need to sample, our sample sizes need to be quite large to kind of account for that. So let's look at a problem here. So the scores on the ACT have a normal distribution where the mean is 18.6 and the standard deviation is 5.9. That's what that notation means right there. That's that the scores are normally distributed. That's what the capital N means. And the first number listed is the mean, and the second number listed is the standard deviation. We've seen that notation before. So we're looking for the probability that a single student chosen at random scores a 21 or higher. So that's our probability statement. We're looking for the probability that the student scores a 21 or better. And the scores are normally distributed. So what would the picture look like? So there is my normal distribution with 18.6 in the middle. I'm going to mark off 21, and I'm looking for this area. Great, so I just need to find the z-score that pairs up with 21. So z, remember, is x minus mu over sigma. So it's 21 minus 18.6 all over 5.9. So my z-score is, and I just have to do the computation on my calculator here, and I get the z-score is 0.407. So now to find that probability there, I'm going to do the normal CDF of 0.407 out to infinity. And remember, well, I personally don't have an infinity button on my calculator. I'm using a TI-84. So I'll do normal CDF of 0.407, comma, and then just maybe like a couple of nines. Use a large number. And I get 34%, 0.342. So there's about a 34% chance that if you randomly chose a student that took the ACT, that student scored a 21 or higher on a particular section. Great, so that's kind of reviewing what we've done before, looking at a distribution that's normal, and where we're talking about randomly selecting just a single person. So now, let's switch over, and instead of just selecting one single person, we're going to select a random group of 50 people. Now, let's think about this for a second. So we're looking at the probability that the mean score for 50 students is 21 or higher. Well, there is only a 30% chance that if I randomly picked a student that they scored 21 or higher. So if I'm going to take 50 kids at random, the chances that the mean of those 50 kids is 21 or higher, that's probably going to be pretty small, because there's only a 34% chance that I pick one kid who scored 21 or higher. So if I'm picking 50 kids, for those 50 kids to have an average that's 21 or higher, that's probably going to be pretty low. So let's draw the picture for what's going on here. So here's the normal distribution, and it's centered at the 18.6 still. But now the key here is that the standard deviation of the sampling distribution is different than the standard deviation of just the distribution of individual scores. So the standard deviation of the sample means here is going to be 5.9 divided by the square root of the sample size, which is 50. So we can see that the larger the sample size, the smaller that the standard deviation of the sample means becomes. So 5.9 divided by root 50 is 0.834. So now I'm going to mark off 21, still looking for that area. But now, okay, when I compute my z-score, okay, yeah, now it's the sample means minus the average of the sample means divided by the standard deviation of the sample means. So that's going to be 21 minus 18.6, but now I'm dividing by 0.834, so the standard deviation of the sample means here is much smaller. So my z-score ends up becoming, since the standard deviation is smaller, the z-score is going to be more extreme. It's going, this 21 is more standard deviations from the mean than in the previous example. So this is 2.88. So now I gotta kind of like maybe go up to the top here. So the probability that my sample mean is greater than or equal to 21, that's going to be, I'll write it over here, normal CDF of 2.88 out to infinity. That's going to be much smaller than the 34%. Yeah, it's 0.002, so it's literally 0.2%. So notice how that there's a much lower chance, but this kind of intuitively makes sense. Sort of the example I think of that's very, very extreme is I think of like just the distribution of all people, and I think of what are the chances if I pick somebody at random that they've won the lottery. Well, that's unbelievably small. But what if I changed the problem to say like, oh, well, what if I pick a random group of 50 people? What are the chances that all 50 of them won the lottery? Well, that's much smaller. That's a much smaller chance than just finding one person that won the lottery at random. And they're both small, but one is certainly even more extreme than the other because you're looking at a group of people. Okay, so let's look at this number 2. So we got this bottling company, and they're filling soda, and the soda is supposed to contain 300 milliliters, but in fact, the contents, it varies a little bit. So in fact, the mean is 298, standard deviation is 3, and the distribution is approximately normal. Okay, but now we want to know what's the probability that the mean contents of bottles in a 6-pack is less than 295. So what would my picture look like? So the mean is going to be 298 here. Okay, there's 295, so I'm looking for the probability that the mean contents are less than 295. So here, I'm looking at I guess I'm assuming a random sample of six bottles. So my sample size here is going to be 6. So the standard deviation of the sampling distribution is going to be 3 divided by the square root of the sample size, which is 6. 1.22, running out of space. Okay, so now I need to compute the z-score for that 295, so it'll be 295 minus 298 divided by 1.22. That z-score should be negative because that 295, that falls to the left of the mean for the population, which is apparently 298. Z-score is negative 2.46. So what am I looking for? I'm looking for the probability that x bar, that I have a sample mean with a sample size of 6 that is less than or equal to 295. And I've already found the z-score there, so to do that I will do normal CDF of negative infinity, so negative and a bunch of 9s, comma, negative 2.46. It's going to be a pretty small probability, 0.007. So there's less than a 1% chance that if I randomly sampled 6 bottles, that the sample mean for those 6 bottles would be 295 or less. Okay, so I think now there's a couple more problems on this sheet. So I think I'm going to pause, and you should try number 3, do the same, and then I will come back and put in the answers to number 3 so you can see if you're following along with this. Okay, so I know the video just picked back up, but hopefully you've tried 3, A, B, and C, like that you paused it and tried to get the answers. So I'm just going to go through them really quick. So during what percentage of years does Ithaca get more than 40 inches of rain? So it says that the rain is normally distributed. Sorry, I just meant to put the pen down there. So very quickly, my picture would look like this. I got 35.4 inches of rain in the center because that is the mean. Mark off 40 inches, so I'm looking for that probability. So it's the probability that in a single year, so probability that x is greater than or equal to 40. So I basically need to find the z-score that corresponds to 40 and then do normal CDF from that z-score to infinity, and we end up getting about 0.137, so there's about a 13.7% chance that Ithaca gets 40 inches or more rain a year. Now Part B was very challenging because we haven't done, well, at least in our class right now, we haven't done one of these problems in a couple of days. But here you had to draw the picture, the normal distribution, 35.4 is still in the middle. But now they're asking us to find the value, how much rain falls in the driest 20% of years. So they're telling me the area under the curve here is 20%, and I put that on the leftmost part of the graph because it's for the driest years. If it was the wettest years, I would have shaded the right tail for 20%. So this is the driest years. So I know that the area here is 0.20. So I'm looking for that x value. So remember, I need to use the calculator to compute the z-score. So I'm going to do the inverse. I'm going to use the inverse normal function. Remember, for that function, you type in all of the area to the left of the value that you're looking for. So this line right above x, I'm looking for all the area under the curve to the left of that cutoff value. So that'd be the inverse norm of 0.20, and that gives me about negative 0.8 or so. That's the z-score. That's the z-score, and then I use the fact that I know z equals x minus mu over sigma. So now at this point you know z, you know sigma, you know mu, you solve for x, and you get that x is about 31 inches of rain. About. Just ballparking this real quick. Okay, now for the last one, the only thing that changes in this last one is that now I'm talking about a random sample of 4 years here. So my sample size is 4. So now my standard deviation of the sampling distribution will be the standard deviation of the original distribution divided by root 4. So that now becomes 2.1 inches. So now I'm just going to do sort of my standard computation. The mean is still 35.4, but now the standard deviation is 2.1 for this particular sampling distribution. And I'm looking for the probability that I get an average rainfall of 30 inches or less. So there's my picture. So I'm looking for the probability that x bar, because I'm talking about the sample mean from a sample size of 4. I'm looking for the probability that x bar is less than or equal to 30. So now I just compute the z-score at 30, run a normal CDF, get about 0.005, so only about 0.5% chance that in a random sample of 4 years, the average for those 4 years would be 30 inches or less of rain. So again, I'll post the PDF, the blank PDF file, right next to the video, and good luck with the sampling distribution.